This is the 4-4 video for the APB class. We're going to talk about section 4.8 here. You should read your textbook in section 4.8 as well. We're going to talk about the normal force. The normal force F sub n is one component of the force that a surface exerts on an object with which it is in contact, namely the component that is perpendicular to the surface. So here's an example of a brick on a table, and the weight, W, straight down, we sometimes call it F sub g. Sometimes we'll call it just mg, because weight is mass times gravity. That force is straight down. And the surface here pushes straight up, the normal force pushes straight up. And we know, since this object is not accelerating, that the normal force is equal to the weight in this particular case. That's true when the table's horizontal, but when we do inclined planes, the normal force does not equal the weight. Here's an example about dealing with normal forces. We have here, it says, the normal force F sub n is greater than the weight of the box because the box is being pressed downwards with an 11 Newton force. So if you look over here, we have the weight of the box is 15 newtons. We're pressing down with 11 newtons, so those two forces downwards are equaled out by this normal force from the surface, 26 newtons upwards. In part B, picture B, the normal force is smaller than the weight because the rope supplies an upwards force of 11 newtons that partially supports the box. So we have this downwards force of 15 newtons being canceled out by the 11 newton pull on the box, and so now the surface only has a normal force of 4 newtons. Since this box is not accelerating in either of the two pictures, the force upwards has to be equal and opposite to the force downwards. And the force that the surface pushes up against the box with is called the normal force. Weight and normal can be equal on a horizontal surface, but not on an inclined plane. So if you have an inclined plane that looks something like this, and this is going to be important to practice this drawing. Let's say we put a box on this inclined plane, put it right here. What we want to do is talk about what forces are acting on this box. We know the weight is straight down. I'll call that mg, we call it w. We'll get used to using mg quite a bit. The other force here is from the surface, and it's perpendicular to the surface, and that is up that way. That's the normal force, and you'll notice that that no longer is opposite of the weight. The weight is still straight down, but the normal force is tilted with the tilt of the inclined plane. So what we're going to do here is we're going to use a XY axis that looks something like this. We're going to tilt our XY axis. Whenever we tilt our inclined plane, we're going to tilt our axis along with it. And what's going to happen is we break up this weight into its XY components. So it's different than our other vector xy because we've now tilted our axis. So we come along here, and there's our y vector, and now here's our x vector parallel to the inclined plane. If this is theta down here, if that's some angle theta, if you go through the geometry, you'll find out that that is theta as well. The red line is mg, and opposite of theta is going to be called mg sine theta, and adjacent to the angle is going to be mg cosine theta. And so now our normal force, you'll notice, is equal and opposite to mg cosine theta. So instead of being just mg, our normal force now is going to be equal and opposite to mg cosine theta. So breaking this up into its xy components allowed us to find this out. This is going to take some practice on our parts. Pause the video, see if you can draw this picture. I also have it drawn here. This is a better drawing of what we have here. And they used FG as being straight down, F being straight down, and this should be F sub G cosine theta and F sub G sine theta. That angle right there is your theta. So that's just another drawing of the same thing. We'll practice this in class, but you should try to practice this on your own as well. The last thing we want to learn is about apparent weight. Apparent weight is different than what actual weight is. Actual weight is always going to be there from the Earth. If whenever we're on the Earth, we're always going to have this actual weight, but the apparent weight will change. If you think of when you're on an elevator, and the elevator starts upwards, you feel heavier, and then when the elevator comes to a stop at the top, you feel lighter. So this is what we're going to be talking about in terms of apparent weight. Usually the weight of an object can be determined with the aid of a scale. However, even though a scale is working properly, there are situations in which it does not give the correct weight. In such situations, the reading on the scale gives only the apparent weight, rather than the gravitational force or true weight. The apparent weight is the force that an object exerts on the scale with which it is in contact. So the apparent weight is what the scale will read. So here we are, there's no acceleration, our velocity is constant, our weight of 700 newtons is down, our scale weighs 700 newtons. Now in this next case, we're going to accelerate upwards. The bottom of this elevator is going to press up against us, causing the normal force to increase, and our weight stays 700 newtons, but now our apparent weight is 1,000 newtons. There's this normal force upwards of 1,000 newtons from the scale, from the floor, causing us to accelerate. Our forces are unbalanced, and now we will accelerate upwards. 1,000 newtons up, 700 newtons down, we're going to accelerate upwards. The next example is when we accelerate downwards. We have our weight still stays, you'll see our weight still stays 700 newtons, but now the normal force is only 400 newtons up. We are accelerating downwards. The floor is falling out from underneath us. The floor does not push up against us nearly as much. It's only pushing up against us with 400 newtons of force. Our forces are no longer equal, so we're accelerating. In this case, we're accelerating downwards. Now here's something that we don't want to happen. The rope of the elevator breaks. The floor, the elevator and us accelerate in free fall. The floor is no longer pushing up against us. We feel like we're weightless until we hit the bottom of the elevator, until we hit the bottom of the shaft. We're in free fall, but the normal force, our apparent weight here is 0. So in this case, apparent weight and normal force are identical to each other. So here's the 4 situations. If you want to pause and write these down in your notes or so on, please go ahead and do so. Alright, the next thing we want to discuss here is a free body diagram showing the forces acting on the person riding in the elevator of the previous figure. W is the true weight, M times G. Fn is the normal force exerted on the person by the platform of the scale. That's also called the apparent weight. When they ask for the apparent weight, they're asking you to solve for a force. So here's our free body diagram in this case. The normal force is the apparent weight. We just discussed that. And if we take a look and do the summation of the forces in the y direction, we get normal force up minus mg down equals our mass times acceleration. So let's try an example problem. We have here a 95 kilogram person stands on a scale in an elevator. What is the apparent weight when the elevator is A, accelerating upwards with an acceleration of 1.8 meters per second squared, moving upwards at a constant speed, and then C, accelerating downwards with an acceleration of 1.3 meters per second squared. So let's go ahead and draw our person, and then we'll draw the forces acting on him, then we use our equation to solve this problem. So here's our person. It's a 95 kilogram person, so we know that the mg is always going to be 95 kilograms times 10 meters per second squared, 950 newtons. That will stay the same. The apparent weight, the normal force from the floor acting on the person, is what's going to change. That's what we want to solve for this problem. That's what we're always going to be looking for in these elevator problems. So we have, it's accelerating upwards with an acceleration of 1.8 meters per second squared. So let's go ahead and do our summation of the forces equals ma. We have our normal force up minus our 950 newtons down equals the mass that we're dealing with here is 95 kilograms. And we want to work with an acceleration of positive 1.8 meters per second squared. Now the rest of these problems are going to be identical to this. Part B, we're going to plug in 0 because it's a constant speed. Our acceleration is 0. And in part C, instead of 1.8, we plug in for acceleration of negative 1.3. So this setup that we have right here is identical in all three cases, and it's identical in all your elevator problems. So let's go ahead and calculate F sub n. So our answer for that one is 1,121 newtons. Why don't you go ahead and try B and C, pause the video, see if you come up with the same answer. So we'll do our same setup. Like was mentioned earlier, instead of having, we do our F equals ma, everything's all the same except instead of positive 1.8, we plug in 0 right there for our acceleration. And now we just noticed that Fn is identical. We're not accelerating, so Fn is going to be 950 newtons. So that's our answer for part B. Now for part C, all we do is we plug in negative 1.3 for our acceleration. And we'll go from there. So we plug in negative 1.3 meters per second squared. Calculate F sub. We end up with an answer around 827 newtons. And that's your basic elevator problem, how you work with it. And this elevator problem is used in many other instances that we'll practice as well. This is the basic idea of the elevator problem.